Hello and welcome. In this session, we'll be exploring problem number 1235, maximum profit in job scheduling. This problem challenges us to optimize job selection to achieve the highest possible profit, given constraints such as overlapping schedules. Let's dive in and break it down step by step. In this problem, you are tasked with scheduling jobs to maximize your profit. Each job is defined by three key pieces of information: its start time, end time, and the profit you earn for completing it. The challenge is that you can only select jobs that do not overlap with one another. This means, if one job's start time occurs before the end time of another selected job, you must choose between them. Your goal is to determine the maximum profit you can achieve by selecting a subset of non-overlapping jobs. You will be given three input arrays, one for start times, one for end times, and one for profits, and you'll return a single integer representing the maximum profit possible. Now, let's look at an example to better understand the problem. Suppose the start times are 1, 2, 3, 3, the end times are 3, 4, 5, 6, and the profits are 50, 10, 40, 70. To maximize profit, we can select job 0, which starts at 1 and ends at 3 with a profit of 50, and job 3, which starts at 3 and ends at 6 with a profit of 70. These two jobs do not overlap, so we can include both. Adding their profits gives us a total of 120. Notice that jobs 1 and 2 are not selected because they overlap with the higher profit jobs we chose. Here's another example to illustrate the concept further. Imagine the start times are 1, 2, 3, 4, 6, the end times are 3, 5, 10, 6, 9, and the profits are 20, 20, 100, 70, 60. The optimal selection here includes job 0, which starts at 1 and ends at 3 with a profit of 20, job 3, which starts at 4 and ends at 6 with a profit of 70, and job 2, which starts at 3 and ends at 10 with a profit of 100. Together, they yield a total profit of 150. Notice how the selection avoids any overlap between the chosen jobs while maximizing the overall profit. In this example, we have start times 1, 1, 1, end times 2, 3, 4, and profits 5, 6, 4. Here, the best choice is to select job 1, which starts at 1, ends at 3, and provides a profit of 6. The other jobs can't be selected because they overlap with job 1, and their profits are lower. So, the maximum profit in this case is simply 6. This example highlights how the solution must carefully evaluate overlapping jobs to ensure the best possible outcome. Lastly, consider some edge cases. If there's only one job, the output is straightforward, it's just the profit of that job. For example, if start time is 1, end time is 2, and profit is 10, the output is 10. In scenarios where all jobs overlap, you can only select the job with the highest profit. For instance, if all jobs have the same start and end times, you would choose the one with the greatest profit. On the other hand, if no jobs overlap, the output is simply the sum of all profits since you can select every job. This problem requires an efficient approach to handle up to 50,000 jobs, so techniques like dynamic programming combined with binary search or sorting are typically applied to achieve optimal performance. When tackling this problem, one straightforward approach is the brute force method. The idea here is to consider all possible subsets of jobs, calculate the total profit for each subset, and then select the one that yields the maximum profit. However, there's a critical challenge: we need to ensure that the jobs in each subset are non-overlapping. This requires checking every combination, which can be done using recursion or backtracking. While conceptually simple, the computational cost is very high. For every job, we have to decide whether to include it in the subset or not, resulting in 2 to the power of n subsets to examine. This exponential growth in the number of subsets makes the brute force approach impractical for larger inputs. Additionally, the recursion required for this approach consumes O(n) space. While it's a good starting point to understand the problem, we need a more efficient strategy for real-world scenarios. To improve on the brute force approach, we can use dynamic programming combined with binary search. The key insight here is that if we sort the jobs by their end times, we can efficiently determine which jobs can be included in the schedule without overlapping. Here's how it works. First, we sort the jobs based on their end times. Then, we maintain a DP array where DP, I, represents the maximum profit achievable by considering the first I jobs. For each job, we calculate the profit if it is included and add it to the maximum profit of non-overlapping jobs, which we can find using binary search. This allows us to consider each job in the context of previously processed jobs, ensuring efficiency. By comparing the profit of including the job versus excluding it, we update DPI with the maximum value. Sorting the jobs ensures that we process them in the correct order, and binary search minimizes the time spent finding compatible jobs, making this approach significantly faster than brute force. This optimized approach offers clear advantages. It combines the efficiency of dynamic programming with the targeted search capabilities of binary search, resulting in a solution that scales well even for larger inputs. While the implementation is slightly more complex due to the need for sorting in binary search, the performance gain is substantial. The key realization here is that sorting by n times transforms the problem into a series of manageable decisions, where each decision leverages the work already done for earlier jobs. This avoids the exponential explosion of the brute force method while maintaining the correctness of the solution. The trade-offs are clear. The brute force approach, though simple, is computationally infeasible for large inputs. In contrast, the dynamic programming approach with binary search strikes a balance between clarity, efficiency, and scalability, reducing the time complexity to O(n log n). This makes it the preferred strategy for this problem. Despite its efficiency, this approach does have some trade-offs. The reliance on binary search and sorting adds a layer of complexity to the implementation. Sorting the jobs introduces an O(n log n) step, which, while much better than the exponential growth of the brute force method, still requires careful handling. However, these trade-offs are minor compared to the significant performance improvement gained. By combining dynamic programming with binary search, the algorithm minimizes redundant computations and efficiently handles the non-overlapping constraints. This makes it the most practical and scalable solution for this problem. In conclusion, the dynamic programming approach with binary search is optimal, offering a robust balance between clarity and computational efficiency, and is well suited for handling large inputs effectively. The problem we are solving is the weighted job scheduling problem. Here, we are given a list of jobs, each with a start time, an end time, and a profit. The goal is to select a subset of these jobs such that no two jobs overlap, and the total profit from the selected jobs is maximized. To solve this, we use a dynamic programming approach combined with binary search. The first step in this approach is representing the input. Each job is treated as a tuple containing its start time, end time, and profit. Once the jobs are represented, we sort them in ascending order based on their end times. This sorting ensures that when we process a job, all potential jobs that end earlier are already considered, which is a crucial aspect of the algorithm. Sorting the jobs by their end times has a time complexity of O(n** log n). This pre-processing step sets the foundation for the dynamic programming solution. After sorting the jobs, we define a dynamic programming array, or DP array, where each element DPI represents the maximum profit achievable by considering the first I jobs. To begin, we initialize DP0 equals 0, which is the base case since no jobs result in zero profit. Next, we use binary search to efficiently find the last non-overlapping job for each job. Specifically, for a job I, we search for the latest job J that ends before the start time of job I. This ensures no conflicts between jobs. By using binary search on the end times of previously sorted jobs, we can locate J and O log n time for each job. Finally, we calculate the DP transition for each job I. The maximum profit is determined by considering two options: either include the current job, adding its profit to DP(j), the profit from the last non-overlapping job, or exclude the current job and keep DP(I1). Mathematically, this is expressed as DP(I) equals max, DP(I1), profit, I, plus DP(j). By iterating through all jobs, we build up the DP array, and the maximum profit is stored in DP(n), where n is the total number of jobs. The pseudocode for the algorithm begins with sorting the jobs by their end times. After that, we initialize a DP array of size n plus 1, where n is the number of jobs, and we also create an n_times array to store the sorted end times of the jobs. The main logic involves iterating through the jobs. For each job, we extract its profit and start time. Using binary search on the n_times array, we find the index j of the last non-overlapping job. Then, we calculate dp, I, as the maximum of two values, the profit from excluding the current job, which is dp, I1, or the profit from including the current job, which is the profit of the current job added to dp, j. After processing all jobs, the final result, which is the maximum profit, is stored in dp, n. This pseudocode captures the main steps of the algorithm, ensuring both efficiency and correctness. The algorithm relies on several key insights. First, sorting the jobs by their n times ensures that when we calculate dp, I, we only consider valid, non-overlapping jobs. This sorting step is fundamental to maintaining the correctness of the solution. Second, binary search is used to efficiently find the last non-overlapping job for each job. Without binary search, finding this job would take linear time, but with it, the complexity reduces to O log n per query. The problem also exhibits optimal substructure, meaning that the solution to the overall problem depends on solutions to its subproblems, which is why the dynamic programming approach works well here. Additionally, we must account for edge cases. For instance, if there is only one job, the result is simply the profit of that job. If all jobs overlap, the algorithm selects the single most profitable job. For an empty input, the result is 0 since there are no jobs to select. Together, these insights and considerations ensure the robustness of the algorithm. To implement the algorithm, we use specific data structures. The dynamic programming array, or DP array, stores the maximum profit achievable for the first I jobs. This array has a space complexity of O, n. The end_times array is another key data structure, used for performing binary search to find the index of the last non-overlapping job. This array also has a space complexity of O, n. Finally, binary search itself is a critical operation, allowing us to efficiently locate the last non-overlapping job for each job. Each binary search query has a time complexity of O log n. When we analyze the overall time complexity of the algorithm, we find that sorting the jobs takes O n asterisk log n, and performing the DP transitions with binary search also takes O n asterisk log n. This gives us a total time complexity of O n asterisk log n. As for space complexity, the main contributors are the DP array and the end_times array, resulting in a total space complexity of O n. To better understand the algorithm, let's walk through an example. Suppose the input is 1, 3, 50, 3, 5, 20, 6, 19, 100, 2, 100, 200. First, we sort the jobs by their n times, resulting in the same order: 1, 3, 50, 3, 5, 20, 6, 19, 100, 2, 100, 200. Next, we calculate the DP transitions. For the first job, dp1 is the maximum of 0 and 50, which is 50. For the second job, dp2 is the maximum of 50 and 20 plus dp1, which remains 50. For the third job, dp3 is the maximum of 50 and 100 plus dp1, resulting in 150. Finally, for the fourth job, dp4 is the maximum of 150 and 200 plus dp0, which gives us 200. The output of the algorithm is the value of dp4, which is 200. This example illustrates how the algorithm efficiently calculates the maximum profit using dynamic programming and binary search. This Python implementation solves the maximum profit in job scheduling problem using dynamic programming combined with binary search. First, we use the zip function to consolidate the given start time, end time, and profit lists into a single list of tuples. Each tuple contains the start time, end time, and profit for a job. We then sort these tuples by their end times to simplify the scheduling process. Next, we initialize a DP list to store pairs of end_time, max_profit. This list will track the maximum profit attainable at different points in time. Initially, it contains only the dummy pair, 0, 0, to represent zero profit before any job begins. For each job in the sorted list, we determine the latest non-overlapping job by performing a binary search using bisect_left. This search identifies the position where the current job start time could be inserted in DP while maintaining the order. Subtracting 1 from this position gives the index of the latest compatible job. We then calculate the new profit if the current job is taken by adding its profit to the maximum profit achievable with the latest compatible job. If this new profit exceeds the profit stored in the last entry of DP, we append a new pair, end, new_profit, to DP. Finally, the last element in DP contains the maximum profit achievable across all jobs. This approach is efficient, with a time complexity of O(n log n) due to sorting and binary search, making it suitable for the given problem constraints. Here, we start by importing the necessary utilities and defining the job scheduling method. Within this method, the first step is to organize the input data. We take the start times, end times, and profits of the jobs and combine them into a single list of arrays, where each array represents a job. This allows us to manage and sort the jobs more efficiently. We then sort these jobs based on their end times using a comparator. Sorting by end times ensures that we can process jobs in chronological order, which is important for avoiding conflicts and maximizing profit. Next, we initialize a tree map called DP, which will help us store pairs of end times and the maximum profit achievable up to that point. We start by adding an initial entry of 0, 0 to represent the base case where no jobs have been selected yet, resulting in 0 profit. Then, we iterate through each job in our sorted list. For each job, we extract its start time, end time, and profit. We use the floor key method of the tree map to find the most recent job that ends before the current job starts, ensuring that there is no overlap. By combining the profit from that earlier job with the current job's profit, we calculate a new potential maximum profit. If this new profit is greater than the current maximum profit stored in DP, we update the tree map with the new end time and profit pair. If the new profit is not greater than the current maximum, we simply skip adding it to the tree map, as it doesn't provide any improvement. This structure ensures that our DP tree map always holds the most optimal profits at different job end times. Finally, after processing all jobs, the maximum profit can be found in the last entry of the tree map. Since the tree map is sorted by keys, the last entry corresponds to the highest end time with the best profit achievable up to that point. We then return this value as the result, representing the maximum profit achievable by scheduling jobs optimally without overlapping. This approach efficiently balances the need to evaluate all jobs while ensuring we only store and update the most relevant profit data, leveraging the tree map for quick lookups and updates. To start, we are given 3 jobs with their start times, end times, and profits. The first step is to combine this information into a list of tuples and sort it by the job end times. This gives us the sorted list of jobs as 1, 3, 50, 2, 4, 10, 3, 5, 40. Next, we initialize a dynamic programming list, DP, with the base state, 0, 0, which represents no jobs taken and 0 profit. Now, for each job, we calculate the maximum profit we can achieve by either taking the job or skipping it. For the first job, start equals 1 is end equals 3, profit equals 50. We use binary search to find the last job in DP that ends before the current job starts. Since no job ends before start equals 1, we take the base state, 0, 0, and calculate the new profit as 50, which is higher than the current maximum profit in DP. Therefore, we append 3, 50 to DP, updating it to 0, 0, 3, 50. For the second job, start equals 2, end equals 4, profit equals 10, we again find the last job in DP that ends before start equals 2, which is still the base state. Adding this job would result in a profit of 10, which is less than the current maximum profit of 50. Thus, we skip this job, and DP remains unchanged at 0, 0, 3, 50. For the third job, start equals 3, end equals 5, profit equals 40, we find that the last job in DP ending before start equals 3 is the first job stored in DP, which ends at 3 with a profit of 50. Adding this job gives a new profit of 90, which is greater than the current maximum profit in DP. Therefore, we append 5, 90 to DP, updating it to 0, 0, 3, 50, 5, 90. After processing all jobs, the maximum profit we can achieve is the last value in DP, which is 90. This is our output for this example. Now, we examine a new example with overlapping jobs that yield a higher total profit. The input consists of 4 jobs, and after combining and sorting them by their end times, we have jobs equals 1, 3, 20, 2, 5, 20, 4, 6, 70, 3, 10, 100. We initialize DP equals 0, 0, again as the base state. The first job, start equals 1 is end equals 3, profit equals 20, is processed by finding the last job in DP that ends before start equals 1, which is the base state. Adding this job results in a profit of 20, so we append 3, 20 to DP. For the second job, start equals 2, end equals 5, profit equals 20, the last job ending before start equals 2 is again the base state. Adding this job leads to a profit of 20, which is not greater than the current maximum profit of 20 in DP. Hence, we skip this job, and DP remains 0, 0, 3, 20. Next, for the third job, start equals 4, end equals 6, profit equals 70, we find the last job in DP that ends before start equals 4. This is the job ending at 3 with a profit of 20. Adding the current job gives a new profit of 90, which is greater than the maximum profit in DP. Thus, we append 6, 90 to DP, updating it to 0, 0, 3, 20, 6, 90. For the fourth job, start equals 3, end equals 10, profit equals 100, the last job ending before start equals 3 is again the job ending at 3 with a profit of 20. Adding this job results in a profit of 120, which is higher than the current maximum profit in DP. Therefore, we append 10, 120 to DP, giving us 0, 0, 3, 20, 6, 90, 10, 120. The maximum profit achievable is the last value in DP, which is 120. In this final example, all jobs overlap, meaning we can only pick one job at most. The input contains 3 jobs, and after sorting by their end times, we have jobs equals 1, 4, 5, 2, 5, 10, 3, 6, 15. We initialize DP equals 0, 0. For the first job, start equals 1, end equals 4, profit equals 5, no prior jobs end before start equals 1, so we calculate a new profit of 5 and append 4, 5 to DP. For the second job, start equals 2, end equals 5, profit equals 10, the last job ending before start equals 2 is still the base state. Adding this job gives a profit of 10, so we append 5, 10 to DP. At this point, DP is 0, 0, 4, 5, 5, 10. For the third job, start equals 3, end equals 6, profit equals 15, we find that no prior jobs in DP end before start equals 3, so the only option is to calculate the profit by adding this job, which results in 15. We append 6, 15 to DP, making it 0, 0, 4, 5, 5, 10, 6, 15. Since all jobs overlap, we can only select one job, and the maximum profit is the largest profit among the individual jobs. This value is found at the end of DP, which is 15. Therefore, the output for this example is 15. To analyze the time complexity of our solution, let's break it down into individual steps. First, we sort the jobs based on their end times. This involves combining the start times, end times, and profits into a list of tuples and sorting that list. Sorting requires O, n log n, time, where n is the total number of jobs. Next, we iterate through the sorted list of jobs, which is a straightforward operation taking O, n, time. For each job, we also perform a binary search to find the most recent non-overlapping job. This is done using the bisect_left function, which operates in O, log k, time, where k is the size of the dynamic programming list, which can grow up to n. Since this binary search is conducted for every job, the total cost of this step is O, n log n. Now, let's consider the cost of updating the dynamic programming list. Each time we process a job, we may append a new entry to the list if it results in a higher profit than before. Appending a single entry to a list is an O(1) operation, and since this is done at most once per job, the total cost across all jobs is O(n). Combining these steps, we have O(n log n) for sorting, O(n log n) for binary search during iteration, and O(n) for updating the dynamic programming list. Since the O(n log n) terms dominate, the overall time complexity of this solution is O(n log n). Next, let's analyze the space complexity. First, we need to store the jobs as tuples of start time, end time, and profit, requiring O(n) space. Then, we have the dynamic programming list, which stores pairs of end times and maximum profits. In the worst case, each job results in a new entry in this list, leading to an additional O(n) space requirement. Finally, the solution uses a constant amount of auxiliary space for variables such as start, end, prof, and the binary search operation. This constant overhead is O(1). Adding these components together, the total space complexity for this solution is O(n), as the O(n) terms dominate. Let's compare this solution with a brute force approach. A naive solution would involve generating all possible subsets of jobs and checking each subset to find the one with the maximum profit while ensuring jobs don't overlap. This approach has an exponential time complexity of O(2 to the power of n), as each job can either be included or excluded, leading to 2 to the power of n subsets. In contrast, the optimized solution uses sorting, dynamic programming, and binary search to bring the time complexity down to O(n log n). By storing intermediate results in the dynamic programming list, we avoid redundant calculations. Additionally, whether we're looking at the best case, average case, or worst case, the time complexity of the optimized approach remains O(n log n), as the sorting step always dominates. Finally, let's solidify our understanding with a mathematical proof of the time complexity. Sorting the jobs is an O(n log n) operation, as it relies on a comparison-based sorting algorithm. For each job, we perform a binary search, which takes O log n, and since we iterate over n jobs, this step contributes O(n log n) in total. Adding the cost of iterating through the jobs, which is O(n), and the cost of updating the dynamic programming list, which is also O(n), we arrive at the overall complexity. When we combine O(n log n with O(n), the dominant term is O(n log n), confirming that the total time complexity of this solution is indeed O(n log n). When solving scheduling problems, one of the most common mistakes is failing to sort the jobs correctly. Many of these problems depend on processing jobs in a specific order, whether by start time, end time, or even profit. Without sorting, the algorithm might evaluate jobs in an invalid sequence, leading to incorrect outputs. To avoid this, carefully analyze the problem to determine the best sorting criterion. For example, in interval-based problems, sorting by end time often ensures that jobs are processed in a way that minimizes conflicts. Another frequent mistake occurs in dynamic programming solutions, where overlaps between jobs are not properly accounted for. Assuming the profit of the previous job always applies can lead to errors if it conflicts with the current job's interval. Instead, use binary search or similar techniques to find the last job that doesn't overlap, ensuring the state transitions are valid. Another pitfall to watch for is using brute force to generate all possible subsets of jobs. While this may seem like a straightforward approach, it becomes computationally expensive as the number of jobs increases, especially when n exceeds 10. Instead, focus on optimized techniques such as dynamic programming, greedy algorithms, or memoization to narrow the solution space effectively. Additionally, edge cases are often overlooked, which can cause runtime errors or incorrect results. For example, scenarios with no jobs, all jobs overlapping, or jobs with zero profit must be explicitly handled. Testing your solution against minimal and maximal inputs, as well as unusual cases like identical job times, will help ensure robustness. Finally, overcomplicating the algorithm is another challenge. Combining multiple techniques, like merging dynamic programming and greedy approaches unnecessarily, can make solutions harder to debug and less efficient. A simpler approach is often better. Start with a clear plan and optimize only if needed. In interviews, it's important to recognize the underlying patterns in scheduling and interval problems. These often involve dynamic programming or greedy algorithms, with sorting as a prerequisite. Once sorted, solutions frequently require either a linear scan or binary search to address overlapping intervals efficiently. It's also helpful to be prepared to discuss the trade-offs between time and space complexity, as many interviewers will ask you to justify your approach. Key questions to clarify include whether job start and end times are guaranteed to be unique, and what the constraints on input size are. These details directly impact whether a brute force approach is viable or if optimization is necessary. If the brute force solution is too slow, break the problem into smaller subproblems and use techniques like memoization or dynamic programming. Binary search on sorted jobs is another common optimization that you should be comfortable with. This problem is part of a family of related challenges that include tasks like maximizing profit, scheduling intervals, and managing overlapping timeframes. Some related LeetCode problems include maximum profit in job scheduling, 1235, non-overlapping intervals, 435, and meeting rooms 1 and 2, 252 and 253. These problems often share similar patterns and techniques. For example, a greedy algorithm can be used by sorting jobs by their end times and iteratively selecting the earliest ending job that doesn't overlap with previously chosen ones. This approach is efficient, with a time complexity of O(n) log n for sorting and O(n) for selection. However, it doesn't handle profit maximization well, as it focuses solely on minimizing overlap. A more advanced approach is dynamic programming combined with binary search. By sorting jobs and using a DP array to store maximum profits, you can efficiently compute the optimal solution while using binary search to find the last compatible job. This method balances efficiency and accuracy, making it a great choice for profit maximization. Another approach worth considering is recursive backtracking with memoization. This method involves exploring all possible combinations of jobs recursively, ensuring that overlapping jobs are excluded. By memoizing results for previously computed states, you can avoid redundant calculations and improve performance. This strategy is particularly useful when building your solution incrementally, as it allows for a step-by-step implementation. However, it may still be slower than dynamic programming for larger inputs, as the recursive nature can lead to higher overhead. While it's not always the most efficient option, it's a good starting point for understanding the problem and can serve as a bridge to more advanced techniques like dynamic programming. Thank you for joining me in solving this problem. To recap, we used dynamic programming with sorting and binary search to ensure an efficient solution. This problem highlights the importance of optimizing algorithms for real-world constraints, making it excellent practice for interviews. If you found this helpful, be sure to like, subscribe, and keep practicing. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!